This is part 2 of the series Integration, and we're going to start out with solving a basic differential equation using the rules that we've just uncovered in our last part. So we're given this differential equation, y prime equals 2. So let's rewrite that and see where it leads us. So we have y prime equals 2. Now I want to change this to Leibniz notation, so dy dx equals 2. And I want to write this in terms of its differential form. So dy equals 2 dx. Now to solve this, we're just going to integrate both sides. So we integrate this side with respect to y, integrate this with respect to x, and we have y equals the integral of 2 dx. This undoes itself here. And the integral of 2 dx, this is the constant multiple rule, so we pull out the 2. 2 times the integral of dx. And the derivative of a constant 1 is just the variable of integration. So this is 2x plus, remember, this is a family of functions, plus the constant of integration. So this is the general solution to this differential equation. We have several problems to look at, so let's go on and look at the next one. So here we want to describe the antiderivatives of 3x. Which means we just want to take the antiderivative of 3x. So the antiderivative, or the indefinite integral of 3x, our variable of integration is going to be x. This is an extremely important piece. You can't take the integral without knowing what variable you're integrating across. And so here again we have a constant, so 3 times the integral of x dx. Now the next rule we're going to apply may not be obvious at first, but the exponent of this variable is 1. So we're going to be using the power rule of integration. And so we have 3 times, we add 1, so it's x squared, and we divide by that added exponent, which gives us 3x squared over 2. Now, do you see what we missed? I hope you caught it. Always include your constant of integration when you're doing indefinite integration. Remember, indefinite integrals are a family of functions. There is always a vertical shift, so we've got to make sure we don't forget this. This is one of the most common mistakes people make when they're taking an indefinite integral or taking an antiderivative. So this is the antiderivative of this function. Now if you wanted to cross-check yourself, you could simply take the derivative of this and see if you get the original function. So let's pull out the 3/2, and the derivative of x squared is 2x plus 0. These 2's cancel out, so what we're left with is 3x. And that in fact matches our original, so this was the antiderivative. Alright, let's move on to the next problem. So here we have the integral of 1 over x to the third. Now you need to exercise caution here. There is no integral counterpart to the quotient rule for differentiation. That's another very common mistake people make. They look at this and say, oh, let's just use the quotient rule. Well, we're not differentiating here. So what we're doing is matching patterns. And the pattern we're going to try and match here is the power rule for integration. So let's go ahead and rewrite this integral. And we're going to bring the exponent to the numerator. So now we can use the power rule to integrate this. And the way we do it is we add 1 to the exponent. So it's x to the negative 2, and we divide by that new exponent. So this gives us negative 1 over 2x squared plus c. Now these are very subtle properties, so you've got to pay attention to them when you're working through these problems. Notice we included our constant of integration. Now let's look at another problem. Here we have a similar idea to the one before. We have the antiderivative of the square root of x. Well, we don't have to have any special rules for this. This is just the power rule of integration. So let's rewrite again. This is x to the 1/2 power. And so, as we normally do, add 1 to the exponent. So this is x to the 3/2 over 3/2 plus c. Now this denominator is going to swap places. We're going to change this division to multiplication by taking the reciprocal of the denominator. So we have 2x to the 3/2 over 3 plus c. Now you could change this back to radical form. I prefer to leave it in exponential form here because we're going to see other problems where we're going to need that form to do further simplification. So let's go on to our next problem. Okay, so with this one, I'm sure you were just struck with a cold shiver when you saw the trig function, but don't worry. Let's pull out the constant first. So we have 2 times the integral of sine x dx. Now we have to think about this carefully. We know that the derivative of sine is cosine, so the integral of cosine is sine. So that's not going to help us. What function has a derivative equal to sine? Well, that would be cosine. The derivative of cosine is negative sine. Therefore, the integral of sine is negative cosine. So 2 times negative cosine x plus c, which is negative 2 cos x plus c. Now, as you can see, these aren't difficult, but you do have to exercise some caution and think about what you're going to do before you do it, because it's very easy to make a simple error and mess the problem up. So let's move on to our next problem. So to integrate a polynomial function, this function is just the integral of 1. So the integral of a constant is the variable of integration times the constant. We usually don't write the 1 out front, plus c. So this is using that integral of a constant rule that we looked at the very beginning. So let's look at one that's a little bit more involved. Here we're using the sum and difference rule for integration. So what we have is the integral of x dx plus the integral of 2 dx. This gives us x squared over 2 plus 2x plus c. Notice in this one we used the power rule for integration, and in this one the constant rule for integration. So let's move on to a little bit more involved problem. Here we just have a combination. We have a constant rule coupled with the power rule, another constant rule coupled with the power rule, and another power rule, and the whole thing is joined by the sum and difference rule. So as you're going to work through these problems and get more familiarity, you don't even think about the rules. You're just going to integrate each one of these pieces independently and combine them all at the end. And it's not really that dark. It's a fairly straightforward process. So let's go ahead and do this. So we have the integral of 3x to the 4th minus 5x squared plus x dx gives us, add 1 to the exponent, so that's 3 times x to the 5th divided by that added exponent, minus 5, pull out the constant, x to the third, add 1, divide by that added exponent, plus x, add 1, divided by 2. Don't forget your constant of integration. And there's nothing to simplify here, so we're done with this. Let's see what else we have in store. Now here again, don't be sucked into the trap of thinking that we have a quotient rule here. We're going to have to rewrite this and see if we can apply some of our basic rules. Again, the common theme is pattern recognition, recognizing one of the patterns to our basic integration rules. So we can separate this out because we have a monomial in the denominator. So let's go ahead and do that. Let's first rewrite. We have the integral of x plus 1 over the square root of x dx. Let's go ahead and separate this out. So we have the integral of x over x to the 1/2. I'm going to change this to a rational exponent plus 1 over x to the 1/2 dx. And now x to the 2/2 minus x to the 1/2 is simply x to the 1/2 plus x to the negative 1/2 dx. And now we can go ahead and integrate this with just the power rule. So we have x, add 1 to the exponent, 3/2, divided by the new exponent, plus x, add 1 to the exponent, 1/2, divided by the new exponent, plus c. Now, quick simplification. Again, we take the reciprocal of this, so it's 2x to the 3/2 over 3 plus 2x to the 1/2 plus c. Now we can simplify this. Let's give ourselves a little room, and we can pull out a 2/3 x to the 1/2 out of each one of these terms. May not seem so right now, but let's do so. Let's do a 2/3 x to the 1/2. Now this divided by 2/3 x to the 1/2 becomes x plus this divided by 2/3 x to the 1/2. Well, this is a 1, and 2 divided by 2/3 is 3 plus c. So this would be the simplified form. You could change this to radical if you want, but not necessary at this point. So a little bit more involved problem. Now let's work the next problem. Oh, dread and panic, yet another trig function, but fear not. Let's break this monster up and see what we can make of it. So we have sine x over cosine x times 1 over cosine x. Again, we're looking for patterns to match. So sine over cosine is tangent, and 1 over cosine is secant. So we have secant times tangent, tangent times secant. So what we need to think about is what function has a derivative equal to secant tangent? Well, that would be secant. The derivative of secant is secant tangent. Therefore, the integral of secant tangent is simply secant. So as you can see, it's very important that you learn your trig identities and understand the basic rules, because you need to be able to match these patterns to be able to execute these antiderivatives. So as you can see, it wasn't really all that difficult, but we just had to know what pattern to match. So let's move on to the next section.